Assalamu alaikum. Today we will start with part 2 of our lesson Functions Generalities. Objectives. At the end of this video, students will be able to define a centered interval at 0, study and interpret the parity of a function defined graphically and or algebraically. Materials. Be ready. Before we start, we should prepare the following materials: textbook, pens, draft papers, copybook, and calculator. Centered interval at 0. Definition 1. Let I be a given interval. I is a subset of R. The interval I is called center at 0 if for every x belongs to I, negative x also belongs to I. Remark: if an interval I is centered at 0, then it is not necessary to contain 0. In this case, it might be the union of intervals. Example 1. Which of the following intervals is centered at 0? Justify. For 1, I equal negative infinity plus infinity. Solution. 1. I is centered at 0 since for every x belongs to I, negative x also belongs to I, so R is a centered interval. For 2, j equal negative 3, 3, j is also centered at 0 since for every x belongs to j, also negative x belongs to j. 3, we have k equal negative 7 closed, 7 opened. K is not centered at 0 since we have negative 7 belongs to k, but its opposite, which is 7, does not belong to k. For L minus 4, 3 is not centered at 0 since negative 4, for example, belongs to L, but 4 does not belong to L. Negative 5 minus 1, union from 1 to 5. M is centered at 0 even if it doesn't contain 0. Here for every x belongs to M, negative x also belongs to M. For n equal negative 8 minus 2 union 2, 8, this interval is not centered at 0 since 2 belongs to n while negative 2 doesn't belong to n. Parity of a function, even function. Definition 2. Let f be a function defined on a domain D of f. Remember that D of f is centered at 0 if for every x belongs to D of f, negative x also belongs to D of f. We say that f is an even function if and only if its domain D of f is centered at 0 and f of minus x equals f of x. Remarks: a given function defined on a centered interval at 0 is not necessarily even, so we can find a function which is defined on a centered interval while this function is not even. If d of f is not centered at 0, then f is not an even function. So, to have an even function, the domain must be centered. This is a necessary condition to be even or not. Example 2. Given a function f defined on R by f of x equal x squared. Prove that f is an even function. Solution. First of all, the domain of definition is R, which is equal to minus infinity plus infinity. Then d of f is a centered interval at 0. Now we study the parity of f. We check if f of minus x equals to f of x. Here f of minus x equal minus x squared. We replace x by minus x. We get x squared, which is equal to f of x. So the conditions are verified. Now we say that the function f is an even function. Example 3. Given a function f defined on R by f of x equal x squared minus x. Is f an even function? Justify. First of all, its domain d of f is a centered interval. Now we check if f of minus x equals f of x. F of minus x equal minus x squared minus x, which is equal x squared plus x. This is not equal to f of x, so f is not an even function. Application 1. Given a function f defined on minus 4 by f of x equal 1 over x squared plus 1. Prove that f is an even function. Pause the video and try to do it by yourself. Solution. First of all, d of f equal minus 4, then d of f is centered at 0. F of minus x equal 1 over minus x squared plus 1 equal 1 over x squared plus 1, which is equal to f of x. This means that f is an even function. Application 2. Given a function f defined on minus 4 by f of x equal x squared minus 5. Prove that f is not an even function. Pause the video and try to do it by yourself. Solution. D of f equal minus 4, then d of f is not a centered interval at 0, so the function is not an even function. One of the conditions to be an even function, the function must be defined on a centered interval. So we say that it is not an even function. Remark, in this application we have f of minus x equals f of x, but since the domain of definition is not on a centered interval, we say directly that f is not an even function even without checking if f of minus x equals to f of x. Property number 1. Let f be a function defined on I such that f is an even function. The curve C of f has y-axis as an axis of symmetry. If you see on the figure, every point that belongs to the curve, its symmetry with respect to y prime y belongs also to this curve. If we take a point n, the symmetry of n with respect to y prime y is a point n prime that also belongs to the curve. If we take another point m, its symmetry with respect to y prime y is also a point m prime that also belongs to this curve, and so on. Example number 4. Which of the following curves is the graphical representation of an even function? Justify your answer. Please look at the first curve. Here the curve is symmetric with respect to y prime y, since if we take any point on this curve and we make a symmetry with respect to y prime y, the symmetric of this point also belongs to this curve. In the second curve, this is not an even function since the curve is not symmetry with respect to y prime y. Please, we can take as a counter example the point of abscissa 2. Here this point, if we take the symmetry of this point with respect to y-axis, the point is not belonging to the curve. So the second curve does not represent an even function. Application 3. Consider the function f defined on I equal minus 3 and designate by C its representative curve in an orthonormal system OIJ. The following figure shows a part of C. Complete C so that f is an even function. Pause the video and try to do it by yourself. Solution. Since f is an even function, then C has y-axis as an axis of symmetry. Here, in order to complete the curve, we take several particular points as shown in the following figure. Here we take 1, 2, 3, 4, 5, 6 particular points. The first point has its symmetry with respect to y prime y, the point itself. The second point of abscissa 1, the point 1, 0, the symmetry of it with respect to y prime y is negative 1, 0. The point 3, 0, its symmetry is negative 3, 0. and so on. We make a symmetry with respect to y prime y of these points to get the following figure. Here we have the completion of the curve C. We have several particular points. We join the following points to get the whole curve C.